Today I start on important topics related to measure theory, especially in LP space. In previous class, we also discussed some measure and sign measure and properties of sign measure. That means monotonicity properties does not hold in sign measure but hold in measure, and subadditivity property also hold in measure but not hold in sign measure. So today we start from positive set. Okay, positive set in measure. Okay, so we write this definition of that. Let x the script a mu be a, okay, sign measure space, be a sign measure space, and let e and e let e be a subset of x. Okay, let e be a subset of x. Then set e, then the set e, the set e is said to be a positive set, is said to be a positive set. Okay, if first one, e be measurable, e be measurable, and second one, mu a greater than equal to 0 for all a belongs to the script a with a subset of e. Okay, that means we talk about that in any sign measure space, any subset of x, this subset will be measurable, and obviously any subset of this subset measure is greater than equal to 0, that means positive measure. Okay, then we talk about that this set e be a positive set, this set e be a positive set. Okay, not a problem at all. So we now erase that portion and going to further discussion of negative set. Okay, so we write here in this way, just write negative set, and here we talk about that let x a mu be a sign measure space and e be a subset of x. Then the set e is said to be a positive set if e be measurable and mu a greater than equal to 0. But here we write negative set. Okay, negative set, then what happened, e be measurable and mu a less than equal to 0. Okay, for all a within a subset of e. Not a problem at all, I think. Okay, so again we read this one, let x a mu be a signed measure space, let e be a subset of x, then the set e is said to be negative set if e be measurable and mu a less than equal to 0 for all a belong to script a with a subset of e. Okay, now we're going to write definition of null set. Okay, here we write definition of null set. Okay, let x a mu be a signed measure space, e be a subset of x, e is said to be a null set. Okay, right here null set, then e be measurable and mu a equal to 0. Okay, equal to 0 for all a belong to script a with a subset of e. Not a problem at all. We also known about that which one is called positive set, which one is called negative set, and which one is called null set. Null set are those That means we construct some sign measure space, and then obviously we construct one subset E whose subset be measurable, and every subset of this subset measure is 0. Then this one is null set. Okay, this E is called null set. That means then again we talk about that. That means if negative set, then same thing is subset of some measure space x a mu, and that means the subset, then E is said to be negative set if E measurable, and mu a subset less than equal to 0. That means measure of A less than equal to 0, negative values with 0 if A subset of E. Okay, now we're going to some proposition. We erase that portion and going to some proposition. Okay, we write it here, some proposition related to that. Okay, let E be a positive set. Let E be a positive set for mu. Let E be a positive set for mu where E subset of x, okay, and mu be a sign measure, and mu be a sign measure. Okay, then what happens? Then every measurable subset of E, then every measurable subset of E be a positive set, be a positive set for me. Okay, let E be a positive set for mu where E subset of x and mu be a sign measure, then every measurable subset of E be a positive set for mu. Okay, then we write this one now here by the definition of positive set, by the definition of positive set E, by the definition of positive set E. Okay, mu A greater than equal to 0 for all A subset of E and A belongs to this measurable set. Okay, and obviously E be measurable set. Okay, then what happened? Then every measurable subset of E is a positive set. Okay, let F be a measurable subset of E, measurable subset of E. Then what happened? Okay, if measurable subset of E, then if we consider mu A greater than equal to 0 for all A subset of F subset of E, okay, and A belongs to this one, then what happened? Then hence we write about it here, hence here this A B positive set, we write it in short. Okay, I think not a problem at all. Okay, so we just write definition of positive set and F be a measurable subset of E, and then this one is done. Then hence F be positive set. Okay, for me. Similarly, we erase that portion and going to be discussion of another proposition related to that. Okay, Let E be a negative set. Let E be a negative set for mu. Okay. Where E subset of where E subset of X and mu be a sign measure. Then every measurable subset of E be a negative set for negative set for mu. Okay. Then what happened? Obviously right here by the definition of negative set E. Okay, here mu a less than equal to 0 for all a belongs to this with a subset of E. Okay, where E be a measurable set. Okay, now let A be a measurable subset of E. Then what happened? Then mu a less than equal to 0 for all a belongs to this with a subset of E. Hence what happened? Hence a be a negative set. Hence a be a negative set for mu. Okay. Now we're going to be discussion about some proposition. Okay. We also known about that proposition, and now we also discuss about some proposition related to that. Where is that portion now? Write this proposition here. Okay. First, we write proposition. Let X a mu be a sign measure. Space. Okay. Now first, if an be an increasing sequence in this A, then what happened? Then limit n tending to infinity mu an equal to mu of limit n tending to infinity an equal to what? Equal to mu of union of n equal to 1 to infinity an. Okay. Number 2, if an be a decreasing sequence, be a decreasing. We also proved these portions in, that means first discussion in earlier lectures also, but today I just write this one. Okay, decreasing sequence in this script A. Then what happens? Then limit n tending to infinity mu of an equal to mu of limit n tending to infinity an, okay, equal to mu of intersection of n equal to 1 to infinity an if minus infinity less than mu a1 less than plus infinity. Okay, now what happened? Now we're going to discussion of another example. Okay, we're also known about that this one some proposition, and we also discussed in earlier part. Now it is that portion and going to write another discussion. Okay, we known about it, but we write it now. Let E subset of R, okay, and then the outer measure, outer measure mu star, okay, outer measure mu star of E is denoted and defined by, is denoted and defined, sorry, and defined by what happened? We known about that mu star E equal to infimum of summation n equal to 1 to infinity, okay, L of IA, such that E subset of union of n equal to 1 to infinity In, where In is an open interval, In is an open interval. Okay, then what happened? Then mu star here PR to 0 plus infinity Bn outer measure, Bn outer measure. Okay, now again we also known about that, also is known about that E is Leveck measurable if what happened, if mu star A equal to mu star E intersection A plus mu star E intersection A complement, okay, sorry, E complement intersection, okay, for all A belongs to this, okay. Now we also erase that portion and going to discussion about another portion. Write some example, okay. Here, let X a mu, X descript a mu be a measurable space. Okay, and E belongs to this script A. Then what happened? If E2 are closer, be a measurable space, be a measurable function. Okay, define f plus x equal to maximum of fx0 and f minus x equal to maximum of 0 minus fx. Okay, for x belongs to E. Then what happened? Then f plus greater than equal to 0 and f minus greater than equal to 0. Okay, then what happened? Now note that what? Note that integration of E f plus d mu, okay, belongs to 0 plus infinity, and integration of E f minus d mu belongs to 0 plus infinity. Okay, this one not closed, open. Okay, if closed then not a problem at all, sorry. Then what happened? Then we talk about that integration of integration of if f d mu, okay, equal to what? Integration of f d mu equal to integration of e f plus d mu difference integration of e f minus d mu. Okay, if that means exist or may not exist. Okay, then may or may not exist, may or may not exist. Okay, then what happened? Then we erase our portion and write something. Okay, then we write some definition. Okay, this definition is here. We say first one. Okay, a b semi-integral, integrable if integration of e f d mu exist in minus infinity plus infinity. Okay, number two is what? If integration of e f d mu exist in minus infinity plus infinity, open, then a b integral. Okay, that means if semi-integral and if integral. When this one happen, we also now known about that. Okay, so today we discuss so many important topics related to that. Okay, so many, that means positive set, negative set, and related known properties related to measure. Okay, so today I stop here. If anyone get this type of video, please subscribe my channel, and if that means this video is also likable for you and others, then please give likes, and if you have some questions and comments, then write it in comment box. So today I stop here. Please subscribe my channel.